We are going to talk about different types of angles and angle properties that happen inside of circles. So this is opposed to the properties that happen outside of circles, which we'll do in a second video. But for now, you're going to need four circles. And if you need help drawing a circle, just do what I did and use a nice piece of tape or something so that you can draw it. All right. So there's four different types of properties we're going to talk about, but the first we should probably talk about what a central angle is really quick, and then go from there. So a central angle is this angle here that comes off of the center of a circle and it opens up to an arc. And we're going to start using the correct notation for angles. Typically you use Greek letters to use as variables for angles. It's like the X for angles. So we're going to use theta, which is looks like a zero with a line through it horizontally. And so I'll put that over here. This is theta. So theta. So theta is like the X for angles. You know, X you use for sides, you use for any length that you need to find. We use Greek letters for angles. So we'll use theta, and then another one that we're going to use after is the Greek letter phi, which is spelt P-H-I. But you actually say it the correct way, F-E-E, phi. So those are two Greek letters that we're going to use for angles here when we need to talk about an angle as a variable and we don't know what it is. So again, we've got this central angle here. That's what this is called. So a central angle happens in the center of a circle, and then you've got this arc over here, and I'll use the points in the circle to be A and B. The central angle here is going to be equal to the measure of the arc. And so if I write that theta is equal to the measure of arc AB, these are going to be equal to each other. So we have to use measure of arc AB. We can't just use regular arc AB. If we use that with this covered up, this means the arc length AB, like the actual distance you would walk along the edge of the circle. We're talking about the measure in degrees of this arc. Degrees are how you measure these. So one other type of angle that happens with this is called an inscribed angle, and you probably have seen this already, but an inscribed angle is an angle that opens up to an arc and has a vertex on the edge of the circle. So I'll use phi for this to show that I'm talking about a different angle. This angle here, this inscribed angle, we should label it so that we know what it is. An inscribed angle is half as big as its central angle. Half as big as its central angle or its arc. So that's sort of something that you want to make sure you know about an inscribed angle. To write that as an equation, it would be, in this case, phi is equal to 1/2 of theta, which is just saying that this angle is equal to 1/2 of this angle, or it's equal to 1/2 of arc AB. So if this angle was in this case, it looks to be about 100. If this angle was 100, this one would be 50. If this angle was 100, this arc would be 100. Remember, 360 degrees goes all the way around the circle, and so we're just measuring the piece of the arc that we're talking about. So again, degrees, 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 they're all measured in degrees. Okay, moving on to some other ones in circles that we have, some other angle properties that happen. We'll talk about when two segments intersect in a circle. I'm just going to use all the colors here. So we'll talk about when two chords intersect in a circle. So remember, two chords are segments that have endpoints on the edge of the circle. And so we'll say these are angles that intersect in the circle. Created by chords. I guess you could say chords that intersect in a circle. I might not be using the vocabulary 100% correct, but you get the picture. So in order to do this, if we're talking about one of the angles in the circle, so in this case, we could be talking about this angle right here. I'll use theta for that. In order to find that, you can average the two arcs. And so what that looks like when you put it into practice, if this was arc A, B, C, and D, this angle theta would be equal to the two arcs, so measure of AB plus the measure of CD divided by 2. So the angle created by two chords is equal to the average of the two arcs. So the angle equals the average of the two arcs. So if this arc was 30 and this arc was 60, 30 plus 60 is 90, divided by 2 is 45. If this was 20 and this was 80, 20 plus 80 is 100, divided by 2 would be 50. And so you just average them if you want to find out what this angle is. Now, if the angle is at the center, obviously it would be equal to it, but if it's not at the center, which is what the case is here, that's how you find it. All right, we have two more. So another one that we talk about is what happens when you have a quadrilateral that's inscribed in a circle. So you got to draw a quadrilateral. Just pick any 4 points you want on the edge of the circle. It doesn't have to be a rectangle. It can be anything. So I've drawn some weird type of quadrilateral. In this case, when you have a quadrilateral inscribed in this, so I'll say quadrilateral inscribed in the circle, the opposite angles here are supplementary. So there's enough Greek letters to talk about the different ones, but I'll just use the edge of the circle here, not to confuse you with too many Greek letters. So this would mean angle A and C are supplementary and B and D are supplementary. So I would say angle A is supplementary to angle C, and then angle B is supplementary to angle D. So that's another property that's true about arcs and angles inside circles. So if this was, say, 30, then this would have to be 150. This looks to be maybe 90, so this one would also be 90. If this was 100, then this would be 80. So they're supplementary. Remember, supplementary means they equal 180 degrees when you add them together. Again, this is for a quadrilateral that's inscribed in a circle. All right, there's one other one for circles, and it's sort of intuitive, which means, it kind of is not too hard that it would make sense. But so if you have a 90-degree angle on the edge of a circle, let's draw it. Make sure we draw it as a right angle. If you have a 90-degree angle, an inscribed angle here on the edge of the circle, you should know what it opens up to. So remember we said if you have an inscribed angle, the arc that it opens up to is 180 degrees. Well, it turns out that any right angle you have, it goes exactly through the center of the circle. So this property says that any inscribed angle that is 90 degrees opens up to a semicircle. Right, see, it opens up to this semicircle, which would mean that the chord is a diameter. So it always also opens up to a diameter. Opens up to a diameter. So that property it ends up being useful when you might be looking for this, or you might need the radius or something, and you need to know that this is the diameter. And a clue is that if you have an inscribed angle that's 90 degrees, doubling it gives you that this is 180, which means this is exactly half the circle. So that's the idea behind that. So you get these 4 properties. Let's do a quick recap. First one, you got your central angle. Your inscribed angle is half as much as that. And then the arc that opens up here is the same as the central angle and is twice as big as this inscribed angle. We had another property where if you average these 2 arcs, you get the center one. We have a third property which says if you have a quadrilateral inscribed in a circle, the opposite angles are supplementary. And then the last one says that if you have a right angle as an inscribed angle, it opens up to a semicircle, which has a diameter right here. So that's it.